Alright, today we're going to start looking at how we can use trigonometry to calculate missing angles and sides in non-right triangles. So I have here a triangle, and I'm going to label it triangle A, B, C. Remember, we use capital letters for the vertices of a triangle. And then for the side lengths, I use small letters. So opposite angle A would be side A. Opposite angle B, across from it, side B. And side C across from angle C. Now what I'm going to look for here are some relationships between the angles and the sides, and I'm going to do that by using my knowledge of right triangles. So what I'm going to do to begin is I'm going to create a right triangle by drawing a perpendicular line from B down to the opposite side. And I'm going to call this the height of my triangle. And what I'm going to do now is create a couple of relationships involving these two separate right triangles. And I'm going to focus here on angle A. I could say that the sine of angle A, which I know is opposite over hypotenuse, would be h divided by c. And if I wanted to multiply both sides by c, I would get h is equal to c times sine A. Alright, now I'm going to do a similar thing with this right triangle, focusing in on angle C, and I'm going to write the sine of angle C is opposite h over the hypotenuse, which would be A, and if I isolate h here, h would be A times sine C. Now since both of these expressions are equal to h, we could therefore say that C sine A is equal to A sine C. And then I could rearrange this equation in many ways, but I'm going to rearrange it as so. I'm going to divide both sides by A times C to get sine A over A equals sine C over C. And so we have an important relationship here. Now what I could do is I could take my original triangle and I could draw an altitude, a height, from a different vertex. So let's suppose I was to go from vertex C 90 degrees to the opposite side. So this would now be a different height, height 1. But then I could follow a similar procedure to above, and I could set up a relationship, or find a relationship between A and B. And in fact, what I would find if I did that is that I would find that sine A over A was equal to sine B over B. And when you start combining all of these results, what you end up with is an important relationship between the sine of an angle and the side across from it, which we call the sine law, which says that the sine of an angle divided by the length of the side across from it are equal for all angles in the triangle. So here's a nice little animation that shows you this relationship. I have a triangle drawn here, and I've got the sine ratio for each of the angles indicated and the lengths of the side indicated, and then I have the ratio of the sine of the angle divided by the side across. And you'll notice that the ratio in all cases is the same. No matter how I move that triangle, the sine ratio divided by the angle across from it is the same in all cases. So this is an unexpected but important result called the sine law. And one of the great things about the sine law is that you don't need a right triangle in order to use it. Alright, let's apply the sine law to this situation. We have a triangle here, and if you were to calculate the third angle, you'd notice that none of the angles is a right triangle. But we can use the sine law possibly as long as we have at least one angle and side across from one another. So in this situation I have 65 degrees as angle A, and I have 7, let's say, centimeters as side A. So we have an angle and a side across from one another. This is a classic time when you could use the sine law. And what we're asked to find here is to calculate side C, and so we would need to know angle C across from it. So we could use these two parts of the sine law. So let's just put things together here. We would have the sine of 65 degrees divided by 7 would equal the sine of 71 degrees divided by C. Okay, it's as simple as that. You don't need to do any kind of thinking of opposite and hypotenuse and adjacent. It's just the relationship of the sine of the angle and the side across from it. Alright, we can multiply both sides. We can cross multiply both sides. So we can get 7 sine 71 equals C times sine 65. Could divide both sides by sine 65. So we're going to type this expression into our calculator. You want to make sure your calculator is running in degree mode. So 7 times sine 71. Close the angle bracket and then close the numerator, divided by the sine of 65. 7.31 centimeters. Now when you're solving these triangles, you want to think a little bit about the reasonableness of your answer. And what I would notice here is that 71 is a bigger angle than 65. So therefore I would expect the side across from 71 to be a little bit bigger than the side across from 65, which indeed it is. Now the other thing you need to be careful about when you are asked to find missing angles and sides in the triangle is how many triangles might be possible with the given information. In the situation above, I was given 2 angles and 1 side. I was given 3 pieces of information. And try however I might like, there's only actually one way to draw this triangle. But there are a couple of situations that you need to be aware of where it's possible to get more than one triangle. And the 2 situations you need to be wary of are if you are given 3 angles. So if I gave you a 30 degree, 70 degree, and 80 degree triangle, and I said draw the triangle, there would be many ways you could draw it, because you might have the 80 there, the 70 here, and the 30 here. Okay, so let's just put 30 here, that looks more like 30, 80, and 70. And I could expand this triangle to be a whole bunch of different sizes. So there's more than one length to each of the 3 sides. There's more than one triangle possible if I simply give you 3 angles. Alright, so 3 angles alone is not enough to confirm that the triangle is unique. There is only one of them, in other words. The other situation you need to be mindful of is when you have a triangle with 2 sides and the angle not in between those 2 sides. Let's suppose you had a triangle in which you had a 10 centimeter length on one of the sides. Another side was 6 centimeters, and the angle not in between them. In other words, any of the 2 angles except this one, because this angle is between the 2 given sides. So let's suppose that this was 30. You need to be careful here because there might be more than one way to draw the triangle. And perhaps you can see that because if I was to take this 6 centimeters and swing it, I could actually have a second triangle created right about there. Let me just draw this out separately. So I could have the 10, I could have the 6 coming down this way, and I could have the 30 degrees. In other words, if I have 2 sides given and an angle not in between them, sometimes there's more than one way to draw the triangle. In other words, the other non-given sides and angles might have different measures given 3 known measures. So you need to be careful about this. The fact that 2 triangles might be possible. And we call this the ambiguous case because we need to be mindful that there might be, in some cases, no triangle, 1 triangle, or 2 triangles. You might wonder, well, how am I going to recognize which it is? Well, I'm going to do an example of that in a minute, and you'll see how that works. Other than AAA and SSA, any other 3 pieces of information will confirm that there is in fact only 1 triangle. So whether you're using the sine law and later the cosine law, if you're given any 3 pieces of information in the triangle, there will only be 1 possible triangle unless you're dealing with 3 angles given and 2 sides and the angle not included given. Alright, we have a triangle with 3 pieces of given information and we want to find angle B. So angle C, let's just position that about here, 24 degrees. So side C would be across from that. 7, let's say. C is 7. And if this is B, this is what we don't know, and we know across from that is 10 centimeters. And so I've got a sketch of what this might look like. And then as I take a closer look, I realize that I have a situation of two sides and the angle not in between them. The angle between the 10 and the 7, right here, is not given. Okay, the angle is in one of the other positions. This is what we mean by two sides and the angle not in between the two sides. And this means that there's a potential of there being a second way to draw this triangle. In other words, there might be two possible angles for angle B. And if I just sketch this, I might realize again, similar to the one I just did, I could maybe swing this side over here, B, so that C was here, and I had a different value for angle B. Alright, let's jump in and see how the sine law will deal with this. You'll notice that we do have an angle and a side across from it, so we can use the sine law. Sine C over C, and then we're talking about side B and angle B, so we could say sine B over B. Let's substitute our numbers into the sine law. So the sine of 24 degrees divided by 7 is the sine of B divided by 10. Alright, so what I need to do is I need to solve for sine B. So I could cross multiply, which would give me 10 sine 24 degrees equals 7 times sine B. Divide by 7. And I could decimalize this in my calculator. And I have sine coming out to be 0.58-ish. Alright, now here comes the ambiguous part of the situation. We know from our study of trigonometry that sine can have a positive ratio in quadrants 1 or quadrants 2. And both of these angles we know have the same reference angle. So when I go inverse sine of 0.58-ish, my calculator says I have a reference angle of 35.52 degrees. That means that my angle B could be 35.52 degrees, or it could be 180 degrees minus 35.52. 144.48. In other words, angle B could have potentially two measures. Now, how do I know whether these are actually possible or not? What you do is you go back and you see, is it reasonable? Could this angle here be 35 degrees? If it was, 35 degrees is a bit bigger than 24, and the side across from it should therefore be bigger than the side across from 24. Well, that's true. Could angle B be 144 degrees? And what you need to look for here is, are there enough measures in the angle left for a third angle? If this was 144 and 24, and you added those up, we wouldn't have 180 degrees yet. So there would be enough measure left over for a third angle. In other words, an angle of 144 degrees is possible. And so in this case, there is two ways to draw this triangle, and there are two possible values for angle B.